Welcome to a quick review on nomenclature, basic chemistry nomenclature. This is not designed to be an in-depth tutorial, but rather a brief overview to help refresh your memory or perhaps explain it slightly differently. There are several main types of nomenclature: ionic nomenclature, which includes binary, polyatomic, and stock systems, which is Roman numerals, and binary molecular nomenclature, and we will discuss all three of those. Binary ionic compounds. They consist of a metal and a nonmetal. To name these compounds, you name the cation first, and you can see by my lovely T there, cation, those are the positive ions. The cations are named first, followed by an anion. The anion is the negatively charged ion, and if it is a single element, the end of the anion is changed to IU. To name a binary ionic compound, you name the cation first, and then name the anion, and that's all there is to it. The name of the metal cation is simply the name of the element. The nonmetal anion names are, the ending of them is changed to IDE. For instance, oxygen becomes oxide. Phosphorus becomes phosphide. Sulfur becomes sulfide. You change the end to IDE. That's how you name binary ionic compounds. Polyatomic ions are named exactly the same way, except you don't change their name at all. You don't change the ending of the name. If you have carbonate that has an APE ending, you do not change that to carbonate. You just keep it carbonate. So it's the name of the cation followed by the name of the anion. So let's take a look. Binary and polyatomic ion nomenclature. We have NaCl. The cation is always listed first. The anion is always listed second. The cation in this case is Na, which is sodium. The anion is Cl, which is chlorine, but the ending is changed to IDE, so it becomes chloride. So the cation is sodium, the anion is chloride. The name of this compound is sodium chloride. The next one, K2O. The cation is potassium. The anion is oxygen, changed to oxide. So the name of this compound is potassium oxide. The next one we have aluminum, Al. F is fluorine, changed to fluoride. So that becomes aluminum fluoride. For the next one we introduce polyatomic ions. We have Li, which is lithium. CO3 is carbonate. So the name of the cation is lithium. The name of the anion is carbonate. The name of the compound is lithium carbonate. For the last one, NH4 is the polyatomic ion ammonium. PO4 is the polyatomic ion phosphate. So the name of this compound is ammonium phosphate. Please notice that the numbers in the formula do not matter at all. When you have a binary ionic compound or a an ionic compound with polyatomic ions in it, the numbers do not matter at all when it comes to naming the compound. The same is not true of other types of compounds, but for simple ionic, the numbers within the formula do not matter. Now, when you get to the stock system, the numbers do matter. The stock system is used to name compounds with transition metals in them. Those are the metals in the D block, or the center of the periodic table. The transition metals are called transition metals because they have varying oxidation numbers, or charges, which cannot be determined by their position on the periodic table. Elements in group 1 have a charge of +1, an oxidation state of +1. Elements in group 2 have an oxidation state of +2. Elements in group 17 have an oxidation state of -1 usually. Okay. But the elements in group 3 through 12, they have varying oxidation states, and you cannot determine it by their position on the periodic table. Therefore, we must calculate the charge on the metal by looking at what it is bonded with. For instance, It doesn't even matter what the metal is. In this case, I have chosen the rare material unobtainium, which is symbolized by the symbol X. It could be any metal. I have chosen unobtainium, which is not even on the periodic table, obviously. So if I want to name this, what would the name of the metal ion be? That would be unobtainium. What about O? O is oxygen, and I changed the end of the name to oxide. So I have unobtainium oxide. But because unobtainium is a metal with an unknown oxidation state, I have to figure out what the oxidation state is. I cannot determine that by looking at a periodic table, especially since this one doesn't occur on the periodic table. To do that, I must look at the anion. In this case, the anion is oxygen. So if we look at the periodic table, and we see oxygen is in group 16, it has a charge of -2. Oxygen has a charge of -2. There are two oxygen atoms, or two oxygen ions, in this compound, each of which has a -2 charge. So -2 times 2 equals -4. Because XO2 is a compound, it has a neutral charge. XO2 is a compound. All compounds have neutral charges. If they didn't, they would be compounds, they would be ions. But because XO2 has a neutral charge, the charge on X plus the charge on O, for the total charge on O, must equal 0. Looky there. We have a math problem. X minus 4 equals 0. X, therefore, must have a charge of +4 in order to cancel that out. So, unobtainium would have an oxidation state of 4, making this unobtainium 4 oxide. If we want to try this with a real element, we can do it like so. Mn is manganese. Cl is chlorine. Change the end to IDE. I cannot tell what the oxidation state of manganese is by looking at the periodic table. However, chlorine is in group 17, so it must have an oxidation state of -1. I have 2 chlorines. -1 times 2 is -2. Manganese is unknown, but I know that when combined together, X plus a -2, or X minus 2, is equal to 0. So this must be manganese 2 chloride. This also works with polyatomic ions. Cu is copper, PO4 is phosphate. So if we look at phosphate, I don't know the charge on copper because of its position in the periodic table. But I do know, because I have all the polyatomic ions memorized, that phosphate has a charge of -3. -3 times 2 is -6. And I know that the sum of all the charges must equal 0, or sum of all the oxidation states must equal 0. Now, how many coppers are there? There are 3 copper ions present, each with the same oxidation state. So if I have 3 unknowns, I know that 3 times whatever that unknown value, -6, must equal 0. So then you can use your algebra to rather easily solve for x and see that x is +2. Therefore, this must be the copper 2 phosphate. Copper will have a charge of +2. So there are your transition metals. Using these Roman numerals, this is called the stock system. Most, but not all, of the transition metals have oxidation states that vary. There are approximately 10 elements that do not change oxidation states, but for general chemistry there are usually only 2 that are used. Silver is always +1, zinc is always +2. Therefore, AgCl and ZnSO4 would be silver chloride and zinc sulfate, respectively. They would not be silver 1 chloride and zinc 2 sulfate, because that would be like always referring to you by your first and last name. The 1 and the 2 would be redundant, because anytime you have a silver ion, there will always be +1. And anytime you have a zinc ion, it will always be +2. So you just name it with all the respective names. Silver chloride, zinc sulfate. The final, oops, here's a more practice. Forgot I put this in. More practice. VO3. V is vanadium, O is oxide. What is the charge? V is a transition metal, so it has to have a Roman numeral. The charge on oxygen is -2. There are 3 of them. -2 times 3 is -6. There's 1 vanadium, so that's X, minus 6 equals 0. Therefore, this is vanadium 6 oxide. For the next example, W is tungsten. CO3 is the polyatomic ion carbonate. So this compound is tungsten carbonate. But tungsten is a transition metal, so we need to identify its oxidation state. Carbonate has a charge of -2. How many carbonates are there? There is only 1. So this total is -2. How many tungstens are there? There are 2. 2x minus 2 equals 0. X must be 1. Giving us tungsten 1 carbonate. Now tungsten doesn't actually form an oxidation state of +1. So this compound does not exist. And several of the other compounds listed may or may not exist. But the method that you would name them if they did exist is exactly like this. The last type of naming for basic chemistry is binary molecular nomenclature. Naming molecular compounds uses Greek prefix. This method is the easiest to learn, but you must be careful. Once you learn the prefixes, you will want to name everything with the prefixes because it is just that easy. Avoid that temptation. Only molecular compounds, those are compounds that are covalently bonded together, compounds whose atoms are covalently bonded together, those are the only ones that are named with the prefixes. And the prefixes, 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. Simply state, oops, I was supposed to hide that. Hold on. Simply state the element name with the appropriate number prefix added. Always remember to change the ending to IDE. You don't have to say mono if it is for the first element. For instance, CO2. C is carbon, O is oxygen, but I change it to IDE, oxide, and there are 2 oxygens, so that is carbon dioxide. N2O5. There are 2 nitrogens, so that is dinitrogen. There are 5 oxygens, so that is pentoxide. Dinitrogen pentoxide. There is 1 sulfur. Since it is at the beginning, the first element, I don't have to say monosulfur. I just say sulfur. There are 6 fluorines. I change fluorine to fluoride, and it becomes sulfur hexafluoride. PCl3, 1 phosphorus, 3 chlorines becomes trichloride, PCl3. NH3, that's a tricky one. That's just ammonia. It's named that way because it's old. It's common name. In summation, binary ionic and polyatomic ionic compounds are named simply using the names of the cations and anions, with IDE endings as appropriate. Transition metal compounds are named with the stock system using Roman numerals to denote the charge on the metal. The Roman numerals are not used to denote how many of the metal atoms there are. It is simply what is the charge on the metal. That's what the Roman numerals tell you. And finally, the molecular compounds are named with Greek prefixes. The most common error that I have encountered with nomenclature is using the wrong method to name compounds. To help avoid confusion in naming, you may color your periodic table in the following manner to remind you which type of compound you are dealing with. Okay? So, if we look at a periodic table, see if I can color it. We look at a periodic table. We have the first we have the simple, straight-up binary ionic compounds. Those have a metal and a non-metal. So, we name binary ionic compounds with the name of the cation and the name of the anion. The key is looking at the first element. If the first element is in group 1 or 2, it will be named simply by naming the cation and then naming the anion. Also, remember our exceptions, zinc and silver. Zinc and silver. Aluminum is also not a transition metal, so I like to color that. So, if the first element of your compound is one of these that is highlighted, you will name the compound by simply stating lithium chloride, or strontium bromide, or zinc carbonate, or aluminum oxide. It is just going to be the name of the first element with the name of the second. Next, let's grab our highlighter again. Let's grab a different color, make it a little bit easier to see. Okay. Hopefully that works. Next is the stock system. Okay. The stock system. These are where you would use the Roman numerals. You would have the name of the element, followed by the Roman numeral with the charge on that metal, followed by the second substance with the IDE ending or polyatomic ion ending as necessary. These now, polonium can go either way, but you won't run into too many compounds that have polonium in them. Because the transition metals are the ones whose oxidation states vary, those are going to be the ones with this color. I don't like going over it too much just so we can't see it, and I also don't like the white line. There we go. Right. If it is one of those colored elements, you will name it with the Roman numeral according to the stock system. Now, I will let you know there are about 8 or 9 other elements that I have highlighted in green that do in fact not change. Scandium is always +3, yttrium is always +3, gallium is always +3, indium is always +3. Let's see, there's a couple more. I don't remember what they are off the top of my head. Technetium is always +7, tantalum is +5, hafnium is +4. So there are several others that are included here in green that do not actually get named that way, but for purposes of this, it's fine. Those are the ones you use the stock system. Oops, I forgot the forgot the F block as well. These also. If the first element is one of the lanthanides or actinides, you will also use the stock system with Roman numerals. That leads us to our last section, and these are, when do you use the Greek prefixes? Never use the Greek prefixes unless the first element is one of these. Hydrogen, now notice I'm also highlighting the metalloids. The metalloids are typically named like nonmetals, although sometimes they are named with stock system Roman numerals, and that's fine. I've omitted the halogens because they don't react, they don't form very many compounds. When they do, you would name them with a prefix system. All right, so there you go. Look at your first letter, or look at the first element in your compound, and this will tell you the appropriate way to name it. I will warn you, look out for nitrogen. Be careful of nitrogen. He's kind of a tricky booger. Nitrogen is part of the polyatomic ion ammonium, NH4. If the first element in your compound starts with nitrogen, because it's part of ammonium, you will name it according to the yellow method. And you'll name it, it's just ammonium chloride or ammonium phosphate. But if it's a binary compound, N something O something, N something Se something, N something Cl something, then you're going to use prefixes. But if it's NH4, then you want to use the Reynolds system. Also, be careful of the H, because the H, usually if something starts with an H, it will be an acid, and acids follow their own method of nomenclature. If it's gaseous and it starts with an H, name it according to the purple method, the prefixes. I hope this has helped. For my students, please color your periodic tables and look at something like this. You may choose your own colors, but that's what I want to see tomorrow.